thank you. First of all, I'd like to thank the organizers for inviting me over and for organizing such a splendid conference. So I'm going to talk about something really elementary, something which I call commutativity preserving extensions groups. Why commutativity preserving? Well, I think there's 6 people at our department who work on commutativity preservers. So I just want to basically hang out with them, and so I had to do something similar, right? But the only thing I know is group theory, so basically I did something like that. So, okay, so everybody knows what an extension of groups is. So I'll just recall some basic facts. So you have a short exact sequence of groups, and that's called an extension. And we usually assume that n is abelian. I'll assume that for most of the slides, maybe just in the first few slides, n would not have to be abelian, but otherwise it's going to be always abelian. And so you have a nice action of q on n, so n becomes a q module. Okay? And now let's come to the definition of this commutativity preserving extensions. So these are basically just the extensions of n by q for which every commuting pair of elements of q has a lift in G, which also commutes. Okay? Just a really simple definition. So let's see what can we do with this. So I'll do something really elementary in the beginning. As I said, everything's elementary. So let's see an example. So suppose that you have a group Q. I should maybe warn you that most of my groups are going to be denoted by Q. Maybe just because I find it boring that every talking group theory starts with let G be a group. So I don't know. It's not that boring, but it's just a coincidence. Anyway, so you have a group for which every commuting pair generates a cyclic group. This is obviously, so every commuting pair of elements has a commuting lift. You can always do that, which means that every extension of Q is CP. And which groups satisfy this condition? Well, these groups are fairly known. So in the case of finite groups, well, you have either complicated descriptions. These are groups with periodic cohomology. You can find this in Brown's book. Or basically, this is equivalent to the fact that if you look at Silo subgroups, they have to be cyclic for P odd, and for P equal to 2, they have to be either cyclic or quaternion. And in the infinite group case, you have examples. We also have examples, for instance, free products of cyclic groups. Free group is an example of this, right? Okay, so if you take a special case in the previous example, just take the group which is cyclic of order P, then then you deduce that every extension of CP is CP. Okay, so which means that if you look at the composition series of P group, every finite P group can be built by a series of CP extensions. Okay, it's just that the kernel of the extension may not be commutative at some point. So, well, the same argument, since we had lectures on polycyclic groups, the same argument basically shows that every polycyclic group can be obtained by a finite series of CP extensions. Okay, so you can get a lot of groups by well, you cannot get all the groups, right? Because if you look at the composition series, then you might end up with some simple groups as composition factors, which are not abelian. And then, so maybe you cannot build all groups using only CP extensions. Okay, what about some counter examples? So what about an example of an extension which is not CP? So it's a really simple example. So you just take elementary abelian group of rank 2, elementary abelian group of rank 3. You specify the action of this one on this one by, well, here I'm using right actions because this example was essentially produced with a gap, but more or less I'm going to use left actions. So now this one becomes a Q module, and in the extension you just, well, here you have a commuting relation in the quotient, and in the extension you just specify that these two elements don't commute, so by adding this relation. And this extension is not CP because you have a commuting pair in the quotient, and then if you lift it up, you cannot lift it to a commuting pair, to a pair of elements which commute. Okay. Okay, so what about, well, now we can play, since we have a special kind of extension, right? We can play with the classical theory of extensions. So I'm pretty sure that everybody knows how it works. So I'll just go, this is going to be really easy. This is something you can do. Maybe elementary school is maybe too soon, but okay. Anyway, so this is the definition of equivalency of extensions. We have two extensions of n by q, and we say that these two extensions are equivalent if there is an isomorphism between this group and this group, so that this diagram builds. Okay? And it's not probably surprising that if you look at the class of CP extensions, it's closed under equivalence, which means that if you have something, if you have a CP extension, and if you have something which is some extension which is equivalent to this one, it's also CP. Okay. So the next thing is, well, how do you describe extensions? You probably also know that you look at the equivalence classes of extensions. Here I'm talking about the extensions with a billion kernel. So n is a billion. And you describe this using the cohomology group, second cohomology group, right? Let me recall what this is. So basically this is just, you look at some maps from q cross q to n, which are cocycles. They satisfy this strange functional equation, which is nothing than associativity written in a different way. And you denote by z to qn the set of all such cocycles. It's an abelian group if you define the operation addition on the points. And then you can also define a special kind of two cocycles, which are called two coboundaries. They have to be built from a certain function which goes from q to n, so that your cocycle looks like this, right? And then you have this quotient, which is called the second cohomology group, and this is the result everybody knows, that the equivalence classes of extensions with abelian kernel are determined by the elements of the second cohomology. Okay, so the natural question is, what determines CP extent, right? Yeah, so let's call these cocycles CP cocycles, and this is the definition. So you take a cocycle, and you say that it's a CP cocycle, so if it satisfies the following property. So if whenever you have a commuting pair, this is not surprising because you start with commuting pairs in Q, right? Whenever you have a commuting pair of two elements in Q, there have to exist two elements in N, so that this difference, this symmetric difference, can be written as, well, this is basically just inner derivation or something, first inner derivation, right? And you denote this the set of all such cocycles with Z2CPQN, and this is a subgroup in Z2, and it turns out it's really easy to verify that it contains the coboundaries, which means that you can take the quotient, and the first result is really okay. Still no first result, but this is just an example. Suppose that you have a trivial, this is just an example how this thing looks like in a special case if you have an abelian group, and if it acts on n trivially, then what this means that this difference is going to be 0, right? And this is precisely the definition of X QN. Okay, so this is a special case. This is a generalization of the X factor in a way. Well, what about the, as I said, equivalence classes of CP extensions? That's easy again. That's pretty straightforward to prove. So they are in bijective correspondence with the elements of H2CP. That's just straightforward. You just mimic the proofs of the usual theorem that everything can be obtained easily. Okay. Maybe let's go back to the examples where you had a group where all abelian subgroups were cyclic. And in this case, this thing is actually equal to, because every extension was CP, right? Then H2CP has to be equal to the second cohomology in this example. Okay. Okay. I wanted to, before I proceed, I wanted to recall some other facts about certain things. I want to recall something which is called the Shor multiplier. There's two posters outside, so you already probably know what the Shor multiplier is. I'm also defined something which is called B naught, whatever that stands for. And first of all, I use this notation throughout my presentation. So K of G is the set of all commutators in G, not the commutator subgroup, but the set of commutators. Okay. And now suppose that you have, so this is the definition. So suppose that you have a free group, a group given by free presentation, and define M of G to be this quotient here, okay? And you similarly define something which is called B naught of G. B naught of G is similar to M of G, it's just the denominator is slightly different. So you take all the commutators in the free group which fall into R, which means that they are basically relators of your group, right? So you take all the commutators which are relators and you generate a subgroup by these relators which are commutators, okay? This is a normal subgrouping here, which means that you can take a quotient. Both these quotients are abelian, that's easy to see. And the first quotient is very well known. It's called the Shor multiplier of G by Hopf's formula. This is just the second homology over Z. Okay. What about, so what is this B naught good for? Well, the thing is that a nice property, a nice feature of the Shor multiplier is that it fits into this exact sequence, which is called the universal coefficient theorem, right? So whenever you have a trivial Q module, then you have a split exact sequence, which basically tells you that if you, in order to consider this subgroup, I mean this group here, you just need to know something about the X and Hom of these two groups. Okay, and I guess some of you may expect the next result. So what about if you look at this new cohomology, however you want to call it, just a subgroup in the second cohomology group? Well, you have something similar. It's actually really nice that this one actually embeds in here. So this map actually doesn't, well, it maps in here, but it actually maps in here. This is easy to see because you have, well, you know the definition of X is precisely that this symmetric difference is equal to 0, so that's not surprising, right? But the thing is that the quotient of these two is precisely this thing. So B naught now plays the role of this M of Q. Okay, and again you have a split exact sequence, and the maps are pretty much the same. They're just induced by the maps which come from the universal coefficient theorem. Okay. Well, let's look at the special case. This is a really special case when you take n to be equal q over z, and suppose that q acts trivially on this one, right? Then you know this is fairly standard. This is 0 since q over z is divisible, which means that by the universal coefficient theorem, this one is isomorphic to this one, okay? But if you look at the definition of this H2CP, well, if you have a trivial model, this just means that you are looking at the cocycles of omega, for which omega x2, x1 minus omega x1, x2 is 0, because you have trivial action, okay? And this is really easy to see that this is isomorphic to another group, which is called, I call it bog of G. And this is the intersection of the kernels of restrictions. So you have a restriction map which goes from this cohomology to this cohomology, which is simply, you take a cocycle and you restrict it to a subgroup, okay? And you take the kernel of this map and you take the intersection of over all abelian subgroups, okay? Right. And as soon as you have this, well, this group bog of G has a name. It's called the Cohomology multiplier. This was the name given by Boris Kuniavsky, I think in 2000. I don't know, but I'll let you know later. So it's going to be on the slide. And this group, there's a reason why this is called like this, because there's a theorem of Cohomology from 1987, which says that if you have a finite group, then this group bog of Q, is isomorphic to something which is called the unramified Brouwer group of this field. So what is this field? Well, you take a faithful finite dimensional complex representation of Q. Okay, Q is a finite group, and you take polynomial functions. Then you localize that, so you get a field of functions over V, right? And then this one acts on this one because Q acts on W, and you say that Q acts on C trivially. So you take a look at the fixed field, and well, there is something which is called defined like this unramified Brouwer group. I'm not going to go into details because it's too complicated to explain. But the thing is that let's go back a little bit. see that this one is log of G, right? And this is just a dual of this guy, right? And since these groups are finite, then they are actually isomorphic in a non-canonical way. So this log of G is isomorphic to B naught of G. So B naught, sorry, talking about G, and I'm just like other people. Yeah, okay. So these two groups are isomorphic, right? It's just that maybe this B naught of G, let's go back. B naught of G has a really nice formula in terms of presentations of groups. And I'll come back to later to this. So, and why is this group, why this unramified Brouwer group so important? Well, there's a classical theorem in invariant theory, which is called Noether's problem. And this one actually says, okay, suppose that you take this field, you have the same situation like before, right? And you take this field, this is a field extension, and when Noether asks, when is this field extension stably rational? By stably rational, I mean that, well, if you take sufficiently many variables, have this one, Q, and if you take rational functions over sufficiently many variables, then this is going to be isomorphic to C, so the rational functions over C over sufficiently many variables. Rational just means that this one is only this one is isomorphic to rational functions over C. Okay, this is what is called, or you can say purely transcendental. That's the same thing. Noether already proved that the answer is positive for abelian groups and symmetric groups. Maybe I don't know if Noether did that. Maybe Hilbert did that for symmetric groups. And then in 1972, Artin and Mumford discovered that there is a nice way of, well, at least in one way, you can answer Noether's problem by computing this log of G. Well, they actually had this unramified Brouwer group, which I didn't define, but it's isomorphic to log of G, log of Q. Sorry, okay, it's gonna be, it's Q. G is equal to Q. Okay. Which means, and they proved that this log of Q is an obstruction to Noether's problem, which means that if this group log of Q is non-trivial, then the answer to Noether's problem is no. Okay. Well, if it's trivial, you can't say nothing. You can't say anything. It's just that, well, you have to do something else. You have to be more clever. So this is really a shortcut to proving, to showing that there is a positive, negative answer to Noether's problem. Okay, nice shortcut, and and it has proven to be useful in determining counterexamples to Noether's problem. So the earliest example is from 1985. So Salzman found some groups of order p to the 9 which had non-trivial p naught, which means that the obstruction is non-trivial, and so the answer is negative, right? Later on. 1987, Bogomolov proved the following. So suppose that you have a group which is, I should maybe mention that in order to prove that Bogomolov multiplier is trivial, you can reduce everything to P groups. Okay, by basically the same argument as in the case of the Schur multiplier. If you look at the P part, it embeds into the Bogomolov multiplier Silo sub. So, okay. So that's basically the same as if you just look at P groups, that's just fine. So he proved that if you have groups of order at most P to the 4, then Bogomolov multiplier is trivial. And he also found smaller counterexamples for P to the 6. He also claimed that for groups of order P to the 5, Bogomolov multiplier is 0. I'll talk about that in a second. And on the other way, I should probably mention that since there's lots of people here who are interested in finite simple groups, that Kuniavsky proved in 2010 that if you have a finite simple group, then B naught of G. Here we have G. Yeah, okay. So then B naught is trivial, okay? But that doesn't mean that Noether's problem has positive or negative solution for finite simple groups, and it's widely open for finite simple groups. So Noether's problem for finite simple groups is still open. I think it's only solved for maybe I don't know, I wouldn't bet on that. Maybe A5 and some other small simple groups, but that's it. Okay, on the other hand, well, this was done independently, so by Hoshikang and Kuniowski and myself, 2012, we actually realized that there are groups of order p to the 5 which are, for which the Moller multiplier is not trivial. And these are precisely groups which have class 4. Okay, all groups of order p to the 5 and class 4 have non-trivial Moller multiplier, and there are subgroups of this. Okay. Okay, so there. There are further applications of B0 which have been discovered recently. For instance, I don't know. I should warn you that I don't know much about this. I'm just going to go through this because I want to do some advertising, but otherwise, just read what it says and then believe me. Well, maybe just pretend I know what I'm talking about. So Martino in 2013 studied something which is called Heckedal invariants, and these are also related to Luther's problem. And he found out that one of the lowest of these invariants is actually isomorphic to B0. Okay, and the Widow in 2013 considered something which is called isomorphism classes of soft braided outer equivalences of the Trimfold center of a finite group, and these can be described in terms of B0, and this has applications in conformal field theory. Then something which is more familiar to group theorists, so Kang and Kuniowski in 2014 found some relationship between B0 and something which is called rigidity. So a finite group is a rigidity if every class-preserving automorphism, so every automorphism which preserves conjugacy classes has to be even. Okay. And last but not least, this is the most recent thing I'm aware of. So this is a paper by Andrei Heikin, my student, Vanya Zernik and Rodriguez, and they proved, well, they found counterexamples to something which is called the fake degree conjecture. So this was a conjecture posed by Isaacs, and this was something which is basically on a conjecture on character degrees of groups of this type. So take finite dimensional nilpotent algebra over a finite field, take 1 plus j, this is a group, right? And then you want to find out something about degrees of irreducible representations over C. And, well, basically, the conjecture was that these degrees can be obtained by the Kirillov orbit method. And Andrei Heikin managed to produce counterexamples in characteristic 2, I don't know, quite long, well, not quite long time, well, some time ago. But he didn't find any counterexamples of odd characteristic. And my student was giving a talk on at the conference about this B0, and Andrei Heikin was sitting in the audience, and suddenly he realized, well, this is exactly what we need. So he invited my student over, and then they produced this. So they have a counterexample now for every prime characteristic. So whenever you have a group which has a non-trivial B0, this one produces, in a way, a counterexample to the fake degree conjecture. I'm not going to talk about this because this is his work, so this is not mine. I'm going to spend some time talking about calculations of B0. So this was state of the art in 2009. So Chu, Hu, Kang, and Kuniowski computed Cohomology multipliers of all groups of 64, order 64, and they found out that there was 9 of these which have non-trivial B0. Okay. And, well, and I think the paper was something like 40 pages long. Everything was done by hand using this original definition of B0. Well, the thing is that you can, now that you know that this B0 is isomorphic to this thing with the Hopf formula, so you have a Hopf formula. For this one, right? So you take the usual thing as in the Schur multiplier, and then you take all the relations which are the commutators, and you factor out this thing. Now you can actually produce an algorithm which works particularly well with polycyclic groups. So suppose that you have, well, let's just talk about finite groups here. Suppose that you have a group with a PC presentation, and then from this presentation you can compute this thing, which is sort of like a central extension of this one, right? Like almost like a free central extension. You just need to add some tails, which means that all the relations which are 1 in your original group are equal to some extra generator. Then you add some extra generators to your group, but then you also need to find extra relations which appear, and this is something which is called consistency check. And this has already been done by Bettina Eichert, Wagner and Nico, 2008. So we started with this one, so we already got this for free, which was good. And now from this one you can actually compute this one, because now you know the only thing you need to do is you have to look at these commutators in here, which map, well, you have a homomorphism from here to here, right? And you just have to look which of these commutators in this group map to 1, and you add these relations. You add these relations to your group, and then you have this f over whatever that denominator is. And then it turns out that B naught of G is just isomorphic to the torsion subgroup of this one. This is an abelian group. You can easily compute this. And this algorithm works really well with finite solvable groups. Now you can compute B naught of G for fairly large P groups, for instance, or other solvable groups. I should probably mention that Graham wrote an algorithm for computing B naught of G for every finite group G, and this is already now a part of HAP. So you can, so now we just install GAP, load package HAP, and then you just use this command. Probably there should be Q. Q is equal to G. Yeah. So yeah, so now you can play with this. Okay, let's go back to this business with CP extensions. This was just an intermediate thing. And first, I should probably recall what Isoclinksm central extensions is. So this is something really classical. So you have 2 central extensions. I'm only going to be dealing with central extensions from here on. So if I don't mention what kind of extension this is, it's just going to be central. And we say that these 2 extensions are isoclinic if you have isomorphism between this group and isomorphism between the derived subgroup of this group, okay? So that there is a commutative diagram where these maps are basically commutator maps. You may be wondering how this map is defined. Well, these are basically cosets of G1, right? But since the extension is central, this is well defined, so everything is okay. And yeah, this is how it's defined. As I said, it's well defined. And this is a nice thing about CP extensions. So suppose that you have 2 extensions which are isoclinic, and if the first one is CP, then also the second one is CP. That's a nice thing, which means that you only need to consider CP extensions up to isoclinism, right? So equivalency is okay, but now you can consider isoclinism, everything by isoclinism. And here is a theorem which basically somehow describes how many of these isoclinism classes of CP extensions there are. So basically, what you have to do, you have to look, well, B naught again comes into play. What you have to do is you have to consider the action of the automorphism group of Q on the subgroups of B naught. With the action is the obvious one, so you take the induced map, this B naught of E is just induced map, and you act with this map on this one, you get another subgroup of your B naught, okay? And this is it. You just take a look at the orbits, and you count the orbits. And for instance, if B naught is 0, right? Well, then you only have one isoclinism class of CP extensions. That's for instance. Okay. So now let's do something. So the goal, when we started with this thing, the goal was to obtain a theory which would be similar to the theory which relates the Schur multiplier with extensions. And that's where you, in that case, you have something which is called a covering group. Right? And now we wanted to do something similar for this type of extensions. And this is what we do here. So first, I'll just recall that if you have a central extension, this is called stem extension. Whenever this one maps, well, this one is a subgroup in here, the derived subgroup of G. Okay, and everything is really easy to prove. It's totally elementary. So every central CP extension is isoclinic to a stem CP extension. So now you just need to find stem CP extensions. And well, there is particular kind of extensions you want to have a look at, and these are called CP covers. Okay, so you look at the central CP extension, and you look at those in which the kernel of the extension has the same order as the Cohomology multiplier. If you remember the theory of the Shor multiplier, this is precisely what is called the cover of the group, right? And there is a reason why this is called a CP cover. So there is a complete analogy between this case and the Shor multiplier case, and I should probably admit that the proofs are all the same. So didn't have to. So yeah, so this is you just rewrite everything in a different language. It's really easy to write papers like this. So suppose that you have a group with a pre-representation. Then well, you define this group, which was already on the previous slides. And well, if you have if you have a stem CP extension which is central, then G is actually a homomorphic image of this one. So all the extensions are actually images of this one. You can obtain all of them by quotienting this one. And if you look at this end, this one is actually an image of this one, which means that B naught is precisely, well, all the kernels are of order at most B naught, the order of B naught of Q. Okay, which sort of makes, which also sort of gives a reason why it's called a maximal extension. It's just that we still don't know if such an extension exists, which would have the order of the kernel precisely the order of B naught. Okay, I think that appears on the next slide. Okay, suppose that CP covers exist. Okay, suppose that you have a CP cover. We still don't know if they exist. Then N has to actually be isomorphic to B naught. So there is not much choice for the kernel in the case when you have CP covers. And also, yeah, this is just a corollary of this. So CP covers are precisely central CP extensions where the kernel has maximal order. This is a corollary of 1 and 2. And what about the existence? Well, you can actually construct CP covers, like in the case of Shor multipliers. And again, the proof is pretty much the same. So again, I have nothing new to say here. So suppose that you have a group given by a free presentation, define this one, and also define this one, so R over this KF set by R. And well, first of all, yeah, so this is just the same thing as in the Shor multiplier case. So A is a finitely generated central subgroup here, and if you look at the torsion subgroup, I use that in my in the algorithm I described before, that the torsion subgroup is isomorphic to B naught. And well, here you have a construction of a CP cover. This is precisely the same as in the case of Shor multipliers. So you take the complement of this one in here, and you take the quotient of this H by this complement. And this is, and in this way you get a covering group. Okay. And this is just yeah, this is just a consequence now. So how do you get all the CP covers of Q? Well, basically you have to look at the kernels in the cocycles in the kernel of this phi tilde map, which is the map which comes from the universal coefficient theorem. If you remember that theorem, universal coefficient theorem. Well, you just that instead of that n, you have to use this B naught of Q. Okay. So basically, if you look at the kernel, you look at the cocycles, and these CP covers are represented by these cocycles. It's just that they may be isomorphic, so you can't really count them by up to isomorphism. Okay. And yeah, here you have a corollary, which is basically follows directly from this universal coefficient theorem, because the kernel of this map is precisely the image of the map which maps from the X to this H2CP. And this is precisely and this one embeds in there. So this is the upper bound for the number of CP covers. And this is precisely the same as in the case of Schur multipliers. If you look at the perfect group, it has a unique CP cover. Okay, so there are some properties of CP covers which are different than the properties of the usual covers, the covering groups, and I want to point out two of these. So the first one is that if you look at the Cohomology multiplier of a CP cover, it's always going to be trivial. This is not the case with the Schur multiplier and the usual cover. You have a simple example. So you take the Schur cover of the elementary abelian group of rank 2. This is just the unitriangular group. Dimension 3, and the Schur multiplier of this one is CP cross CP, so it's not trivial. Okay? The other one is that all CP covers of isoclinic groups are isoclinic. In the usual case, when you have Schur multipliers, you just know that covers of a given group are isoclinic, right? But you don't know about what happens when you have isoclinic groups and you look at all the covers in the isoclinic family. But here, all the CP covers of isoclinic groups are isoclinic. And again, you have a counterexample. As I said, you have a counterexample. You just take two abelian groups, let's say CP square and CP cross CP. They are isoclinic. Well, the cover of this one is CP square, and the cover of this one is, again, the triangular group, which means that the covers are not isoclinic. Okay. We also looked at something which is called the minimal CP extensions, and minimal CP extensions are just the extensions where the kernel is a cyclic of order P, and we call this minimal CP extensions. And basically, you can describe this extension by this object here. Just have a look at this CP cohomology, however you want to call it, of Q over FP. And we proved, we basically described this group. So this group is elementary abelian rank precisely the number of generators of Q plus the number of generators of Cohomology multiplier. So basically, you have this is sort of a description of minimal CP extensions. Okay. Well, there is a nice application, because if you have a minimal presentation of a given group, and you look at, and suppose that this thing is the minimal number of relators that generate R as a normal subgroup of F, which means that you have a minimal presentation. And now you look at among these relators, you look at those which are commutators in the free group. Okay, and you count those, and then you can prove that the rank of this bin out of G is less than this difference minus the number of generators of Q. Why is this good for? Well, this one helps you prove that B naught of certain groups is trivial, because if you get something strange here like 0, right, then this one's going to be trivial. So, and it's actually quite useful. For instance, if you look at the group of unitriangular matrices, there is a nice minimal presentation with n-1 generators, which have order P, and all other relators are commutators. Which means that if you plug in, you have n-1 generators, and you have n-1 relators which are not commutators, and all the other relators are commutators, which means that, well, this thing here is going to become 0, right? Oh, sorry, no, it's just number of, because what is this thing? What is this thing? This difference is actually the number of relators which are not commutators, right? So you have n-1 generators, and you have n-1 relators which are not commutators, and you plug in these two numbers in here, you would get 0 here, which means that the Cohomology multiplier of unitriangular groups is trivial. And this was also proved by Mihailo in 2013 using some different tools. It's actually also in here, because Fried and Volklein actually proved that. It's a funny fact that I haven't seen that before. I just noticed that in the book on the first Galois problem by Male and Mansart. So there's, it follows from there that if you take the Bogomolov multiplier of a sure cover, it's always trivial. Okay, another example is braid groups. Well, braid groups have relations. Well, this is a presentation of a braid group, and you have relations which are basically commutators, right? These are relations are commutators, and you have relations which are not commutators. And you have a presentation with n-1 generators and n-2 relations which are not commutators. And then if you plug in these numbers in there, you will again get that the B naught of braid groups is. Okay, now for the rest of the talk, I'm going to talk about something which is called the commuting probability, and it turns out the commuting probability is also closely related to B naught. So just to remind you of what this is, well, basically this is just the probability that the randomly chosen pair of elements in G yields. So this is basically this quotient here, right? And it's well known, it's easy to prove. It was noted by Erdős around 68 that this is actually the quotient of the number of conjugacy classes by the order of G. Okay, so this is a little bit nicer formula for the commuting probability. And it's an exercise to prove that if the commuting probability is bigger than 5/8, then it has to be 1. And it's a really easy proof. You just use class equation, nothing else. And then you just estimate things in a really straightforward way. It's an exercise. I leave it to the audience. If anybody solved it, 3 minutes. Okay. Well, the thing is that the general idea is that if the commuting probability is high, then you will have a lot of commuting pairs in. That's my intuition, right? You will have a lot of commuting pairs in G, which means that there will be a lot of these guys, commutators which fall into R, right? Which means that this thing is going to be fairly large, which means that the Bogomolov multiplier is going to be fairly small. And you can actually prove a result of this kind. This is what we proved in 2013. That if the commuting probability is bigger than 1/4, then Bogomolov multiplier has to be trivial. This was kind of hard to prove. This was done by by considering minimal counterexamples, and then it took like 20 pages of. It was too technical, so I don't want to talk about it. We actually produced more accurate bounds if you just consider P groups, but I skipped that. And there is a really nice characterization of CP extensions in terms of the commuting probability. So a central extension is going to be CP precisely when the commuting probability of this bigger group is going to be equal to the commuting probability of the small group, which is not surprising, right? Because you're just lifting commuting elements to commuting elements in the big group, right? So this is also one way of verifying whether or not your group is right. And okay, so this is just a corollary. Well, this is basically just because. Now we're talking about G. Okay. This is just because you take the cover group, the CP cover group, and the CP cover group has the same commuting probability as the original group, but the B naught of a CP cover is 0. So that's why you can get, which is basically somehow, this is somehow a counterpart to this result, right? Whenever you take any probability which appears as a commuting probability of a given group, there's going to be at least one group which has Bogomolov equal to 0. And this is my last slide. Since lots of people, there's at least one or maybe 2 slides, two posters, poster sessions which talk about the orders and sure multipliers. I should probably start with this. So what we figured out is the following, that basically, if you look at the order of the Bogomolov multiplier, you can somehow bound it in terms of a function of, well, first you consider only groups for which the commuting probability is bigger than epsilon, right? And then you can bound the order in terms of this epsilon, and well, basically you also have to look at the generators of CILO subgroups and take maximum of numbers of generators. And which is maybe a little bit more surprising is the following, that if you look at the exponent of B naught of G, it can be bounded in terms of the commuting probability only. This is something which is maybe surprising. And just the last corollary, the thing is that if you look at the exponent of the Schur multiplier, it turns out that the exponent of the Schur multiplier is at most the exponent of your original group times the exponent of B naught. This is just a corollary. So you can bound the exponent of the Schur multiplier in terms of this constant, which depends only on the commuting probability and the exponent of Q. Maybe I should mention that I've been pursuing the problem whether or not the exponent of the Schur multiplier divides the exponent of Q for, I don't know how many years. It seems to be an open problem. There are some counterexamples, but fairly few. And this seems to be one of the closest, because it sort of looks like a linear, well, constant times the exponent, right? But this constant still depends on, okay, pretend that it doesn't depend on anything, and then you have almost a nice one. So, okay, thank you, Dan.
One or two questions?
Yeah, that's hard. Yes, there are, yeah. There are some isolated points, and there's also some points, accumulation points. So that's still not well known. Yeah, it's still, I think it's still open. I don't know, because I've seen that there was a preprint which was supposed to classify. Two classes were left. I don't know. I haven't heard from those people ever since they posted preprint on archive. So I don't know. Maybe they're still left. I haven't tried anything.